Matriculants, welcome to Learn Extra Live. This is your show. You own it. Learn more, learn extra with us. My name is Abram, and I'm not alone, of course. I'm with Phil. How are you, Phil?
I'm great, thanks to you, Abram.
I'm feeling well. It's a women's month. I should feel well. You know, women are just everything. Whether it's science, whether it's maths, women are just all over. There's a quote that says, "Women are an architect of everyone's life."
Oh, no, fair enough. We've all got to say thanks to our moms.
Of course. What are we doing today for everyone?
Well, today we're taking a look at the electromagnetic spectrum. Now, that sounds like a whole big mouthful, and it is, but it's really not that bad. And it's actually one of my favorite sections of science.
All right, if it's your favorite, it's also my favorite.
Fantastic.
And it's, of course, Mindsetter's favorite too. But let me tell you what, Mindsetters, you can join us, chat with us on Facebook, ask us some questions. We have a whole bunch of 49,000 Mindsetters that are there on Facebook talking to us. Join them and let's help one another. Our Facebook page is facebook.com/LearnExtra. Like the page. Also, you can follow us on Twitter @LearnExtra. Lastly, you can download your notes for free on learnextra.co.za/live. They are for free and they are proudly sponsored by Macmillan. So enjoy the show because it is for you.
Fantastic.
Thank you, Phil.
Well, let's take it away. Well, Matrix, this is one of my favorite sections of physics because this deals with the electromagnetic spectrum. Now, this bunch of words over here behind me is talking about the range of frequencies of electromagnetic waves. Now, none of this might make sense to you if you haven't finished your syllabus in school yet, or if you're starting to get into, okay, what are light waves or radio waves or microwaves? The really cool thing about this is the electromagnetic spectrum, guys, is affecting you right now. You're using the electromagnetic spectrum to see me. You are using the electromagnetic spectrum to actually get the satellite signal or whatever signal you're getting us on. Now, guys, this is hugely important, and this is one of the most amazing sections. And once again, we're going to be playing around with some of those online simulations. We're also going to be teaching you about some simple experiments that you can actually do with your TV remote at home. So that's something I'm really excited about. So let's jump right into it, the electromagnetic spectrum. Let's see what's on the menu today. Well, starting off with today, we're going to describe now electromagnetic radiation. Now, a lot of you are saying, oh, Phil, radiation, that sounds like bad stuff. Electromagnetic radiation sounds very, very dangerous. Well, guys, it can be, but I'm going to teach you the differences. Now, it's to describe, first of all, electromagnetic radiation as a vibration on electric and magnetic fields. Now, this is where the name actually comes from, and we're going to take a little bit of a closer look at that. So, magnetic and electric fields which are vibrating and traveling at c. Okay, now, guys, you might recognize c. It's the speed of light, and it's always given to you. We're going to talk a little bit about the speed of light. Now, you might say, well, what does light have to do with electromagnetic radiation? It's one of the examples. We're going to get there now. Now, this is the part that I really like, is to identify the types and uses of different EM, which is short for electromagnetic radiation. So we're going to take a look and see where electromagnetic radiation touches us in our daily lives, where you guys use it. I'm busy using EM radiation all the time, every day. I'm very, very happy that I have a piece of my body which is sensitive to some of the EM radiation, and this is what helps me see. And then we're going to start to link the energy of an EM wave, the electromagnetic wave, to its ability to pass through materials. Okay, now this is something which really fascinated me. Since I was a little boy, I was wondering, okay, well, radio waves and light waves, why can radio waves go straight through the wall, but light waves can't go straight through? Well, this blows my mind completely. Or why can I go to the hospital and the doctor takes an x-ray and the x-rays go straight through my muscle tissue, but it doesn't go through the bone? And this is one of the ways that doctors can take pictures inside you without opening you up, and that's really a good thing. I don't like being opened up. Okay, so now let's jump straight into it. Let's talk about why this strange word, this really long, complicated word. Now, just a reminder, guys, I've got some of these pictures, especially in the notes. Jump online. I'm sure there's a link online. Is there, Abram?
It's definitely there.
Fantastic. Okay, so Abram has posted a link online. Get these notes because this picture is a little bit tricky. So what I'm going to do is I'm going to walk you through it very, very slowly because it's quite weird to try and picture inside your mind. Now, there's two parts to this name. It says electromagnetic waves are transverse. Now, remember from grade 10, a transverse wave has a disturbance at 90 degrees to the motion of the wave. So guys, if the wave is headed this way, the disturbance is at 90 degrees. So that means up and down. Okay, but now let's take a look at the two different types of waves which travel together to make electromagnetic waves. So there's a really cool picture over here. I'm just going to scroll down a section, and we're going to draw over it. And we're going to see how to make an electromagnetic wave. Okay, well, one of the ways that we can do this, I'm going to draw this in green, and we can talk about which waves we're talking about. I can see magnetic fields over there. The magnetic fields are vertical. I'm going to draw a line to show the transverse magnetic fields. Now, this might look a little bit complicated, but one of the things that you'll notice is that the magnetic field over here, I'm actually tracing it out as we go. It goes up and down, and it keeps vibrating. Now, that's just how a normal transverse wave actually looks. And guys, you've seen this from grade 10 before. Now, what I'm going to do is magnetic waves, if they've got an electric field vibration with them at 90 degrees to each other, now this is getting quite complex, guys. If they're vibrating together, I have an electromagnetic wave. So there's an electric wave and a magnetic wave. So let's talk about our electric wave now. I've drawn in green the magnetic field. Now let's look for the electric field in this picture. Okay, so I can see an electric picture over there. So let's actually make sure that it's in a different color there. Let's make sure that we can actually see what's going on there. There we go. We've got some yellow. There we go. And I can see that the wave is coming out and going back, and it's coming all the way around and going out and coming back again. And I can actually see these two waves. Now, this is a bit of a challenge for you guys at home. I want you to picture things which are vibrating at 90 degrees to each other. So one is vibrating upwards and downwards, and the other one is vibrating left and right. Now, I want to see if you can do that at the same time. So I've got magnetic vibration, and I've got electric vibration from left to right. So doing them both together looks kind of weird, and it's kind of difficult as well. And this produces an electromagnetic wave. Now you say, well, Phil, I don't run around my house, and I don't play around with electric fields and magnetic fields. But guys, this actually happens all the time. If you've got a cell phone, you're playing around with these waves. If you're seeing me, you're playing around with these waves. This is why these are so important, because electromagnetic waves are so important. They're everywhere, and I use them in everyday life. And now here's the thing. The way that I make these guys is I vibrate these two planes at 90 degrees to each other. I'm not sure that that's clear. So I make vibrations in the magnetic and the electric fields at 90 degrees. It's absolutely vital that you've got these 90-degree vibrations, and then you've got an electromagnetic wave. The only thing which changes one into the other is the frequency and the wavelength of these waves. So all I need to do to change from one type of radiation to another is by changing the length, in other words, the wavelength of these waves. Now that's something that I can actually see on this picture over here. Remember that a wavelength is the length between two parts of the wave which are in phase on the next wave. Now, that might have seemed a little bit confusing, so let's actually draw it onto my diagram here. So I said the wavelength is the distance between two parts which are in phase on consecutive waves. So there we go. I've got my first piece over there. Now let's go and look for another piece of another wave which is in phase. So one wave away, and I can see another wave over here. So I'm measuring it on the electric field. You could have done it on the magnetic field. Not a problem. But there we go. That's the length of one of my waves. Now from grade 10, we should remember that that is lambda. Okay, and that is my wavelength. So guys, all you have to do to change from one type of wave to another is to change the wavelength. Now, these words have found their way into the English language. Guys, when we say tune in, guys, we're actually talking about the electromagnetic spectrum here. The frequencies that you're picking us up on, especially to do with like DSTV and all of the TV reception signals. When you tune into something on the radio, you're actually tuning into the correct wavelength of that particular radio station. So what you're actually doing is you're adjusting your radio to make sure that you're adjusting to that particular wavelength. Guys, this is how amazing the science is. It's becoming real, and you can actually see the waves in your everyday lives. Now, let's move on to the thing which I love the most. Now, this is called the electromagnetic spectrum. Okay, now we've discussed what electromagnetic means. It means that I've got an electric vibration and I've got a magnetic vibration. Now, a spectrum over there is the collection of all the different types, all the different wavelengths. And what we're going to do is we're going to start splitting up the spectrum into several tiny little pieces, and we're going to try and discuss what the uses are for each one of these. Okay, so the different wavelengths and frequencies of electromagnetic radiation are known as the electromagnetic spectrum. Okay, so let's just stop there for a second and discuss some of the words that I can see on the screen at the moment. Now, the first one scares a lot of people. It says radiation. Okay, now let's just get rid of the fear that you've got about this word radiation. Now, this word has actually come up in the media many, many times. Now, radiation has something which has got a very bad name from the 1950s and the 1960s because of nuclear testing and nuclear accidents in Russia. Now, radiation itself can be harmful. Too much of certain types of radiation can be very harmful. But guys, I wake up each morning and thank my lucky stars that I am in the middle of radiation. Now, light is a type of radiation. Radio is a type of radiation. Microwaves are a type of radiation which heats up my food in the morning. Even infrared is that nice, warm, lovely feeling that I feel when I step out the door and I look at the sunshine. Sun shines on me, I get nice and warm. That is some infrared radiation right there. And guys, it is not harming me. We are going to talk about the types which can harm you. So guys, it's important that you get educated as well about the types of radiation that you can experience, which ones are good and which ones are bad, which ones are helpful and which ones are harmful. So now let's take a look and see how the spectrum starts out. Okay, now I've got a very big picture over here. Once again, guys, this is inside the notes with a little bit more detail than I can ever show you, but I'm going to draw some pictures over here. Now, first of all, I noticed that there's two things which I really want to take note of. Remember last week, I told you that electromagnetic waves can carry a certain amount of energy in the particles, and these particles were called photons. Now, what I've got over here is an electromagnetic array. So basically, it's saying I've got a different range of frequencies and a different range of wavelengths. Now, take a look. As I increase the wavelength or drop the frequency, I change the type of wave. Now, you'll notice that those two arrows are pointed in opposite directions. The more energy something has, the less the wavelength. So let's say that in other words. Let's do the converse of that. So the shorter the wavelength, I can see really tiny little short, tightly packed waves over there. Those guys have got the most energy for each photon. Now, just a reminder that that energy comes packed in the form of photons. If you remember from last week, we can calculate it using the formula of Planck's constant times by the frequency of the wave. Okay, so now what's the deal at the other end of the spectrum? What happens when I increase the wavelength? I stretch out my waves. They become longer. So what happens to the energy? I start to lose more and more and more energy. And you might say, okay, well, why would I want low energy waves? Well, that's actually a good thing. Guys, the radio waves that you use for the morning radio, you do not want those interacting with your body. I don't want to feel the local radio station inside my body. I'd like it to enter the car, and I'd like it to go into the radio, and the radio has got a specific set of instruments to pick up those radio waves. I don't want to be listening to the radio the entire day long. Also, certain radiation can cause energy to enter objects. Now, this is what happens when you put your food inside a microwave. Radiation is going into your food and heating it up. I don't want that to happen to my head, okay? I don't want to be cooked. So, guys, the energy is really, really important. We're going to be focusing on the energy a lot when we take a look at that simulation. Now, guys, please, we've been doing it the last couple of weeks in a row. PhET is an amazing site where you can play around with some of the simulations. When we come back from the break, we're going to be playing around with a PhET simulation, and I want you guys to do exactly the same. But before we do that, I want to plant some words inside your head. Okay, so now I talked about the really high energy rays. Those were called gamma rays. Now, as we move backwards, down, 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 we increase the wavelength. Guys, there's something that I'm sure that all of you have heard of before. X-rays. Okay, now X-rays are very, very useful things. I use them inside hospitals. Hopefully you guys aren't getting too many X-rays. That means that you're in lots of accidents. X-rays are really important. We're going to discuss the uses of all of these in a moment. Then we move down, and you might recognize this, ultraviolet. Now, I've probably heard that inside adverts for sunscreen and protective skin products, and ultraviolet is sometimes abbreviated as UV. Now, that I'm sure you've seen on products before. Something which protects you from UV tends to be a very good thing. Now, here's the really sad thing, guys. This tiny little section over here, a teeny tiny section of the spectrum, is what I see as visible light. Guys, every color that you can see, the entirety of my body, the entirety of your TV screen, and everything around you that you can see fits into this teeny tiny portion of the EM spectrum. You can only see this tiny little slice of the electromagnetic radiation. And that is every single color in the rainbow that you can see. And you might actually recognize this looks a lot like a rainbow because that is the full length of visible light. From blue right down at the bottom at 400 nanometers, right the way down to red light at 700 nanometers. Guys, every color that you've ever seen fits into this tiny little portion. So whenever somebody tells you seeing is believing, well, guys, they're believing a very small amount of things because there's so much of the electromagnetic radiation that you just cannot see. Our eyes are not built to actually pick up those other types of radiation. But I'm very thankful for this very tiny little piece of radiation I can see, because I can see, guys, my eyes are working. It allows me to do my job. It allows you to see me. And I can write on this beautiful board in all of these colors. And this is all due to this tiny little piece of the electromagnetic radiation. Okay, now there's a couple of others that you might not know about. Okay, infrared. We're going to be talking about infrared in a little moment. Guys, you all experience infrared. You all use infrared. Infrared is very often called heat rays. Now, infrared is a type of radiation which comes from the sun. When you go out into the sun, you feel that nice warmth on your skin, especially in winter here on the Highveld. Right, I like some infrared on my skin. That means that I'm warming up in the sun's energy. And there's lots of infrared. If you sit next to the fire, you're receiving lots of infrared. And then we move right down. Now, there's a teeny tiny slice right at the end of infrared, which doesn't appear on this picture. Now, guys, right at the end of infrared, you'll actually notice something which you might recognize, something called microwaves. And I've put it into the notes as an extra little piece. Now, microwaves, wait a minute. Phil, what are you talking about? You can't be talking about appliances. Now, one thing that I've noticed is that people must misunderstand why they are called microwaves. A microwave is the box. Really? How do I cook food using a box? Well, guys, the radiation inside a microwave is actually called a microwave. So the radiation inside there, now you can be really smart when your mom's cooking some food, or your sister, or you cooking up your own food. I'm hoping so. So microwaves over here fit into the band between infrared and then, guys, here's one that almost everyone has heard of, radio waves. Guys, everyone knows what a radio is. A radio is a way to get radiation and make use of it. I get information, news, all sorts of things over the radio. But guys, I think it's time for a short break. I'm getting too excited here.
Let's get cooking. You know what? I love it when science meets the reality. It's just so fun. I love it. And you know what? Through this show, I'm so enlightened. So many things that you're talking about, it's real life coming into existence through science. I'm learning a lot from that. Otherwise, my sisters, I hope you're learning as much as I do. See you after the break. Don't go. Welcome back, Matrix. Now it's time for us to take some questions over Facebook, and let's see if people are learning and they understand.
Fantastic.
Right, we have a first question, which is from Masilo Matsepula. It says, what happens to the rays when the wavelength is decreased then?
Okay, well, guys, mindset is, even if you know the answer, I want you to think about how you might answer this. Guys, it's always a sign that you understand something when you can explain it to somebody else in simple language. If you say, oh, it's complicated, it means you don't really understand it. Okay, so they said, what happens when I decrease the wavelength? So in other words, we're moving across to the shorter wavelengths on this side. Now remember, what happened was, when I moved in terms of wavelength, let's actually move down to the shorter wavelengths, right down at the end here. Okay, so now those short wavelengths have got the most energy. But now there's other things happening as well. Remember that when you decrease wavelength, I noticed that the waves are vibrating very, very quickly. That means that the frequency has increased as well. So the frequency will increase, and therefore the energy also increases. So the shorter the wavelength, the higher the energy and the higher the frequency of those waves. Really nice question.
Right, and then here's another one from Twendani Chiomodivani. What is spectrum?
Okay, this really weird word. I don't use it all the time. Okay, now I generally don't use this word spectrum. Okay, now we talked about electromagnetic, but when I talk about spectrum, the spectrum is the collection of all the different types of waves. So when you talk about a spectrum, you talk about the entire collection from short wavelength to the end of, from short wavelength to the end where there's longer wavelengths. So that entire collection from radio waves to gamma rays, that is my spectrum. It's all the different types of things which I can find. Really nice question, guys. I'm really liking that you're interacting on the page. Thank you so much.
Yeah, keep them coming if you don't understand, and let's help one another.
Absolutely. Well, guys, let's get back into it. Before we went away from the break, we started learning about all these different types of waves I didn't even know about. Now, the reason that I don't even know about them is because I only see this tiny little portion. I've actually expanded it out to make the full rainbow of color here. Now, guys, just to use that word again, down at the bottom here, I've called this visible light. Now, guys, from blue right the way down to these beautiful colors of red, that is called the visible spectrum. It's a collection of all the colors that I can see with my eyes. Now, my eyes have got 4 different types of cells which allow me to see all of these. The rods and the cones, and these actually allow me to see all of them. For those of you doing life sciences, the cones are the ones which pick up the different colors, and there's actually a small percentage. Now, since it's Women's Month, here's an interesting fact, guys. Okay, 1% of women have actually got a mutation inside their eyes which give them a special type of cell in the back of their eyes, specifically to pick up the color yellow. They've actually got an extra type. They've got 5 types of cells. So guys, don't argue with the women about color because they know. They know the color.
But what happened? What's the whole concept behind women liking pink as compared to yellow?
Guys, I think they just have their preferences and don't argue with it.
All right, leave it to them then.
Absolutely. Okay, well guys, here's the really amazing thing. All that richness, all that beautiful stuff in nature is all fitted into this tiny little portion of the electromagnetic spectrum. So this is a tiny little spectrum of light that my eyes can actually see. It's the range of light that my eyes are sensitive to. From 400 nanometers at the blue end to 700 nanometers at the red end, this is all of the colors of the rainbow. Guys, most of you have seen a rainbow before, and this is where the colors actually come from. But that's not all, guys. There's so many other different types of electromagnetic radiation available to us. And guys, scientists have been very clever. They've actually found ways to use all of these, and some of these we actually need to stay away from because some of them can be very, very harmful to us. We're going to talk about them in bits and pieces. I'm going to give you some tips on how to protect yourself from some of the bad types of radiation, how to use the good radiation, and actually how to pick up some things which your eyes cannot see. So we're going to start running through them, and we're going to start taking a look at these different types of radiation and what we can actually use them for. Okay, so now let's split it up into tiny little pieces, and pieces which we can use. Okay, so guys, this table is inside the notes, right? If you're writing this down furiously, do yourself a favor, just download the notes. Macmillan sponsored them. It's looking really good, and we can actually see this table. I can see everyone's already, you've already posted.
It's also on Facebook.
Guys, it's on
download
Facebook.
it as an image.
It's fantastic. Now, a lot of matrics ask me, it's like, Phil, do I have to remember all of these wavelengths? No, guys, just relax. All you have to do is put them into order. So we're going to start at the long side of the wavelength. We're going to start with the long waves, the really nice, easy, slow motion waves, the really long waves. In fact, sometimes these waves are as big as 100 meters long. 100 meters is very big for a wave. Now, it's kind of difficult to picture a 100-meter long wave, but remember that all of these travel at the speed of light, guys. Okay, and that is 3 times 10 to the 8 meters per second. Every type of radiation over here is all traveling at the speed of light. The only reason I call it the speed of light is because light is the one which I can see. Okay, and the irony is, there we go, c is the constant that we use for the speed of light. So that's 3 times 10 to the power of 8 meters per second. So that is the speed of all of these waves. Now let's run through them and let's just discuss what types of wavelengths we get and what we use them for. In a moment, I'm going to make use of one of them, and guys, this is one of those experiments that I want you to do. Now, to take part, all you're going to need is a TV remote, a little bit like this one, and your cell phone camera. I want your cell phone camera to be turned on, because I'm actually going to use a studio camera, and we're going to see one of these electromagnetic waves in action, and you cannot see it actually with your naked eyes. And this is a really cool experiment. So I have a TV remote, or any other remote which has got a little clear spot over here, and you'll actually notice that this is an LED, guys. You should all know what LED stands for from grade 11. So now an LED in the front here and a cell phone camera, and that's what you're going to need. Some of the cell phone cameras I've noticed don't work on this, especially the Apple cell phones don't work particularly well this way, but all of the others seem to work very, very well with this. Okay, so guys, just have these ready. I'm going to ask you to pick them up in a moment. Okay, so let's start going through our electromagnetic waves. Here we go. We're going to start out with radio. Now, radio are the really, really longest type of electromagnetic waves. And guys, there's some very, very useful ways of using radio waves. I use them first and foremost here for communication. Guys, of course you know about communication. You say, okay, well, I don't use a two-way radio. Guys, radio waves are the way that I receive news. It's the way that we actually receive stuff on the radio. This is why it's called a radio. It uses radio waves. Okay, now this next one is a little bit more tricky to understand. They use radio waves in certain types of medical imaging. Now, if you want to get really fancy and you want to impress your mom, you can start talking to her about something called NMR is the one, or nuclear magnetic resonance imaging, or sometimes it's called an MRI. So it's magnetic resonance imaging. Now this is what happens when they want to take a look inside your body and take pictures. They use radio waves to tell where the hydrogen atoms are inside your body. Very clever type of imaging, and they're actually managing to use radio waves to take these incredible pictures. They can see what's going on inside your body without harming you, without opening you up, without harming any of the cells. It's a very safe type of imaging, really nice, but it is very, very expensive. And also there's another trick to this. They use very large magnets over here in radiomagnetic imaging, and these magnets obviously attract metal, so you've got to take off all your jewelry and whatnot before you go inside an MRI scan. Okay, now microwaves, guys. You all recognize what microwaves are. Those are those boxes that make food hot. Okay, now those are very short wavelengths. You'll notice that these wavelengths are getting shorter and shorter. It's slightly shorter than radio. Now you might actually say, okay, well, where do I use microwaves? I don't heat up my food all the time. Guys, at airports use something called radar. Now radar uses microwave frequencies. Radar is a way that airplanes can tell where other airplanes are. It's also a way for the airport to tell how close the airplane is. So radar is a very important use for microwaves. And of course the other one, which is cooking. Okay, now guys, there's actually a third use, and I'm actually going to scribble this in because, guys, I constantly see you on these. Now at the short end of microwaves, what you'll actually notice, sorry, it's actually on the long end of microwaves, around about a centimeter wavelength, is cell phones. Now, this particular use of radiation has got a lot of people really worried about, you know, what happens when I use a cell phone next to my head? Is it safe to store a cell phone on my body? Guys, at the moment, there's no proof that there's any link to cancer, but that word radiation has got a lot of people scared. So I say, okay, well, I use microwaves to cook things, and my cell phone gives out microwaves. Wait a minute, is a cell phone cooking my head? Guys, no, it's not. Microwaves have got a certain frequency specifically designed to wobble water molecules inside your food and heat it up. Cell phones work on a different wavelength. They might cause a little bit of warming around the ear, but guys, at the moment there's no conclusive proof that there's any link to cancer. In fact, cancer rates are dropping while cell phone use is going up. So before people get a little bit too excited about this, it's a really nice project to go and research the effect of microwave radiation, specifically from cell phones, to see if there's any health danger. Okay, now this is the one that I particularly like, infrared. Okay, you might say, okay, well, infrared, that sounds kind of close to red, and that's what the word actually means. Infrared means it's just beyond red. Okay, so now infrared has got these slightly shorter wavelengths from microwaves. Now, you might say, okay, well, where do I use infrared? Well, you might have actually used one today, and that is specifically in the case of TV remotes. Okay, now guys, we're going to do a short experiment together. We're going to use TV remotes. Now, TV remotes have actually got a little infrared light on the front. Now, guys, I'm going to ask you to turn this away from the TV because I don't want you to turn me off. or at least pick up another remote that's not going to switch me off. Please don't switch me off. Okay, now what I want you to do is to pick one of the buttons over there, and you can guard it away from the TV, and I can point it at my eyes, and if you press the buttons, guys, I'm not seeing anything at all. My eyes cannot pick up what's going on. I can see Abraham's trying this out for himself.
Yeah, I'm also trying.
That's fantastic. Okay, so now these remotes over here, I cannot see anything else. Now guys, I want you to pick up your cell phone camera. Now what you can do is point your cell phone camera at the end while you're pushing the button. Now what you should see, if you're lucky, is a tiny little bright flashing light over here. I'm actually going to walk up to our studio camera and show you exactly what I mean. So guys, don't be scared. I'm walking towards you. I'm not going to fall out of your TV. So here we go. Right, there we go. And what you should actually see is this really nice little bright flashing light. Now that bright flashing light at the front there is the infrared light which is coming out of the front of this remote. Now it's a really cool experiment, and you can actually amaze your parents because you cannot see the light out of here, but my cell phone can see this because my cell phone is not my eye, and my cell phone might actually be a little bit more sensitive than my eyes. So it's a really nice experiment to show that I can't see everything with my eyes, so seeing is not necessarily believing. I can't see this, but I believe it because it can switch me on and off. Please don't switch me off, guys. Okay, so really nice experiment using infrared light. Infrared light is a type of radiation. Okay, well, Abram, are you busy trying yours?
Yeah, I've been trying, but I don't think is there anything?
Okay, well, let's see if you walk towards the camera.
Is there anything?
Fantastic. Okay, well,
I just believe.
There we go. Now he believes.
Yeah,
okay, now he's seen and he's believed it. Okay, so now there's infrared rays going from his remote into the camera, and the only reason that you guys can see it is because our camera can pick up infrared light. The cell phone camera can also pick up infrared light. Really cool way to check if your batteries are flat as well. So if you're worried about this, the remote, its battery, no, you amaze everyone at home, pick up your cell phone, point the camera, and start playing around.
So going to try that.
Fantastic. Okay, so there we go, guys, science in action. Okay, so let's start flipping back to our different types of electromagnetic radiation. Okay, now guys, this next one you might not know too much about, but guys, when you watch those movies of those army guys and they're busy watching the bad guys and you see everything's gone all green, what you're seeing there is an example of something called night vision. Now infrared rays, remember, are just an example of heat rays. Now everything has got a little bit of heat on it, different temperatures for different objects, and infrared is a good way to see in the dark. Now there's special cameras that these soldiers are wearing that can do the same thing as your cell phone is doing. And now what happens is those cameras are using the infrared lights from warm bodies like people to actually see in the dark. You don't need any visible light to see in the dark because there's still lots of infrared available. And this is a really nice way to actually see animals and other people inside the dark without using any visible light. And this is also the way that cameras work when it's very, very dark. Some television programs actually show you this. They usually show it up as green, which is a bit confusing, but that's just the false color which has been put over by that computer. Okay, now next on to my favorite type of electromagnetic spectrum over here, visible light. Guys, these are the colors which I can see. The blue down here at 400 nanometers, the 700 nanometers of red, and everything in between. Everything in between there fits into this tiny little narrow patch which I can use my eyes to see. All those 3 different types of cones in the back of my eyes, or some lucky ladies have got 4 cones, one specifically for yellow. And this is my most important and most favorite use for that type of radiation. And that's how I see, and that is vision. Okay, obviously plants are quite keen on visible light as well, because plants use visible light to do photosynthesis. Guys, without photosynthesis, you would have no food on the table, right? Everything you eat depends on photosynthesis. So some pretty important stuff. If I couldn't see and eat, life would be quite difficult. So the small piece of electromagnetic radiation is hugely important. Okay, now onwards to the ones. Now these are the ones that I'm going to tell you to stay away from. Okay, now we've all heard about ultraviolet, or we called it before the break, we called it, what was it? UV. Okay, now let's actually write that in pen so you can see. Okay, so now UV, we've heard this before. Now, ultraviolet light is actually really useful stuff. Now, especially if you start to take a look at some of the new money, right, that we see, and you hold it underneath a UV light or an ultraviolet light, you've actually got patterns on there which you can see, but only under ultraviolet light. It's very useful for money identification. So guys, if you're running a business and if you're worried that the money that the people are giving you is false, what you need is a money identifier with a UV light, because the Reserve Bank has put on a very special marking to make sure that you can only see this under ultraviolet light. And now this is something else that not a lot of people know, is that bees specifically can see ultraviolet light. And flowers use ultraviolet to actually attract bees. So that's one of the other uses for ultraviolet light. Now there's many others. Ultraviolet light is used to sterilize medical equipment because it kills things. Okay, now that's one of the reasons that should be a red flag. Guys, stay out of the UV light. Okay, what about the next one? This next one we've heard of before. X-rays, guys. Okay, the uses. Now these are fairly obvious. Medical uses, or the medical images. Guys, many of you have been for X-rays. X-rays go through my body and stop on the bones, and from behind I can see a shadow. And that tells doctors where my bones are and where my joints are. So if I've got a broken bone, I can see it using X-rays. Guys, I'm getting too excited about this, and I'm forgetting to give you guys a little bit of a break to go to the bathroom, write down notes. Let's take a short ad break.
And I have some questions for you. Yeah, let's take that
so
break.
many.
Yeah, and you know what, Mindsetters? Shocking news are that we're only left with 82 days, 5 hours before the main exams on the 28th of October.
Wow, guys, feeling the pressure right here.
Only
I'm sweating
82
for you.
days. Hope you're up and ready, but we're giving you our best, so use it. See you after the break. Welcome back, Matrix. Now it is that time where we take your questions and see what we can get over. Remember, also, you can take some Curie assessment, and Phil is going to be telling you more about that, how they can help you also to see, are you learning a lot? Where are you struggling? So it's very much important that everybody takes those assessments. But I have the questions for you, Phil.
Oh, fantastic. Let's answer them.
Right, the first one is from Siabulela Stofile. It says, are microwaves and gamma rays different types of radiation? Please explain.
Absolutely. Okay, now we talked about radiation. Radiation is a disturbance in the electromagnetic fields which move away from a point. Now microwaves and gamma rays are very different. Now microwaves are longer wavelengths. I find them below visible light. They're much longer. We've just discussed them. I use microwaves to cook things inside the microwave oven. I use them for radar. But now gamma rays, we're going to get to gamma rays in a short little bit. And I just want to see if we can go back there. There we go. All right, so now gamma rays are particularly dangerous. They are a very different type of radiation. Gamma rays have got a very, very short wavelength. And guys, can you think of what that does to the energy? Gamma rays have got a very, very high amount of energy. That means that gamma rays are very, very harmful. Okay, so guys, you've got to be very careful of gamma rays, but microwaves, on the other hand, are very useful inside the kitchen. I use them to find out where planes are. Not too much of a problem. All right. I hope that answers that question. There were a couple of others, weren't there?
Here's another one from Ayamokhosi J. Khaile. He says, how are these electromagnetic waves made?
Okay. Now, electromagnetic waves are made in one way and one way only. Okay, now, this might seem a little bit strange, but what we're going to do is I'm actually going to draw something out. We're going to draw what happens to an electron. Okay, now, a reminder when you're trying to accelerate an electron. You might say, why would I try and accelerate an electron? Guys, anytime you try and make electric current, you are accelerating electrons. Let's say I make a positive and a negative pole. An electron begins to move in the direction over there, from negative to positive. If I accelerate an electron in that direction, what I'll do is that's already the disturbance in the electric field. Now, from grade 11, we know that any movement of electrons is going to make a disturbance in the magnetic field around it. So what you'll find is that there's a disturbance happening around that electron. So what you'll actually find is that I've got this disturbance on the magnetic field which goes around that electron. Now, as the electron bounces up and down, backwards and forwards, we get the magnetic turning at right angles to it as well. Now, the short answer to that is I move electrons, I vibrate electrons and accelerate them in opposite directions. Okay, bit of a complicated example and idea, but it's the only way to explain how I make an electromagnetic wave. But now it goes even further. What happens? How do I decide if I want to make a radio wave or visible light? It depends on how quickly you accelerate the electrons back and forth. Now, to make visible light, how do I switch on a torch, for instance, and that makes visible light? Or how do I switch on a walkie-talkie and that makes radio waves? That depends on how quickly you can accelerate the electrons back and forth. So a radio wave is really slow acceleration, light wave really, really fast, and you actually start noticing that you have to accelerate smaller and smaller and smaller things to make the shorter wavelengths. I hope that answers that question. Are there any others before we move on?
I think we can move on for now.
Okay, all right. So now we were on this page and we were talking about the electromagnetic spectrum. Let's just finish it off before we get to the exam questions over here. All right, now here we go. Now, in terms of these last couple, we were talking about X-rays. Now, X-rays are very useful at the airport and in the mines. Now, because X-rays can shine directly through bodies, they can see if somebody is hiding away something valuable like gold or diamonds, and if they're trying to steal them from the mines, or if you enter an airport and you're wearing a weapon like a knife or a gun or some explosives, they can see immediately what's going on your body. Okay, so X-rays are very useful for security. Now, gamma rays. We had a question about gamma rays. Now, gamma rays are the shortest wavelength of all. Now, in your daily life, there's a tiny bit of gamma rays coming down from space, but it's a very small amount. Guys, gamma rays are so high energy. In fact, I use gamma rays to kill things. Usually to kill the bacteria inside my food, so I sterilize food. If I want food to last for a very long time, especially for the military, I use gamma rays. Sometimes gamma rays are used for medical instruments to make sure that there's no viruses or bacteria or fungi living on the instrument. Gamma rays are very effective at killing everything inside here. Now you might say, okay, well, if gamma rays are so good at killing things, I might want to keep them away from me. And that's absolutely true. Okay, and the other thing that they're actually very well used for, and this is one of the things that South Africa is very good at doing at the moment, is in cancer treatments. Doctors use gamma rays to shoot cancer cells, to kill those cancer cells and actually treat patients. Now, the one thing that you can actually do is you can focus those gamma rays down to a very fine point and make sure that you're only damaging the cancer cells and not the patient's tissue. Okay, so I hope that sort of wraps up the different types or uses of the electromagnetic waves. I don't think we've got too much time to talk about transmission and absorption of these things. But one thing I wanted to sort of impress upon you is that electromagnetic radiation is always made up of photons. Now, just a reminder of these photons, remember that photons are particles, and particles can interact with matter and give away energies. Okay, now I'm not going to get too deep into this because we don't have a lot of time, but what I wanted to talk to you about was the relationship between the energy of the wave and the frequency. We know that energy of a wave is equal to Planck's constant times the frequency. Or we know that it's Planck's constant multiplied by the speed of light divided by, sorry, we're busy shifting across there, okay, divided by the wavelength. Now, there we go. Right, divided by the wavelength. So I'm noticing that there's two ways to calculate the energy of a photon. Okay, so the frequency of the light affected, but the thing that I'm really concerned about here is the wavelength. Now, how does this relate to what we've been saying? Well, guys, this is direct. The energy of those waves is directly related to their wavelength. The shorter the wavelength, the higher the energy. And this is where I really want to impress upon you something very, very important. Guys, these three types of radiation down at the bottom here are the most dangerous. Now, UV rays, X-rays, and gamma rays are so high energy. Guys, these can do the photoelectric effect on your body. Now, what does that actually mean? You're saying, okay, well, the photoelectric effect, that doesn't happen to me every day. Guys, it is happening to your body, and it's very bad for you. The photoelectric effect is when high energy radiation comes into your cells and knocks electrons away. And you say, okay, well, that's not a big deal. I lose electrons all the time. But guys, if you start losing electrons from your DNA, electrons, remember, are the glue which hold together molecules. And that's a really bad thing. They're causing damage to those cells. So UV, X-rays, and gamma rays have got a collective name. Those three can make ions inside your body. These three are called ionizing radiation. They make ions by knocking electrons off your cells. Now that's really bad for you. Ionizing radiation is terrible for you. And you should do whatever you can to protect yourself from this. Now, lucky for us, the sun isn't shining too many X-rays, and most of the X-rays are stopped by the outer atmosphere. Ultraviolet light, however, is a big problem because there's a lot of ultraviolet light present in sunlight. UV light, lucky for us, the planet has natural sunscreen. And I just want to show you something using one of these PhET simulations. Now, this PhET simulation shows us different varieties of light and UV and visible light. And what we can actually see over here, I'm going to change this down to ultraviolet light, and we're going to talk about a molecule called ozone. You might have heard of ozone before, because ozone is 3 oxygen particles next to each other. I'm going to shine UV light on it, and we're going to see why ozone is so important. If I shine UV light, so let's just move that across. There we go. Right, let's see if we can move that across, and let's actually have our UV light. There we can see UV light approaching our molecule, and what you'll notice is that occasionally the UV light doesn't go through, and you can actually see the ozone has broken apart. Now what it's done is it's actually protected us. So we've got ozone which protects us from UV light. The energy from the UV is used to break up ozone, and it just creates more oxygen. And that's really useful for us. We're not breathing in that oxygen, but that UV light is not falling down to the planet. So I know that ozone can protect us from UV light. So that's fantastic. I'm really glad that there's ozone in the atmosphere and that it's protecting me. Let's move onwards with the questions. Okay, guys, these are all in our notes, and I'm going to be answering these bit by bit. I particularly like this because it starts to talk to us about the different types of radiation. Now it says, which one of the following shows electromagnetic waves in order of increasing frequency? Okay, so there we go, increasing frequency. I can see there's an E missing over there. Alright, so that's from the exam question. So it's increasing frequency. Now let's just analyze this. Increasing frequency means decreasing wavelength. So decreasing wavelength. Okay, so that means decreasing wavelength. What does that mean for us? Okay, well guys, I should know which ones come first. Okay, so let's read through our options and let's see what goes on. Okay, so I'm looking for decreasing wavelength. Now, X-rays, let's answer our first one. X-rays, then UV rays, then infrared, then visible light. Guys, that doesn't even seem like it goes in the same order. And X-rays have got a very short wavelength. Now that's going from a high frequency, in other words, a short wavelength, downwards. So option A is definitely out. Let's take a look at the next one. Infrared rays. Those are fairly long wavelengths. Okay, so we're looking for something. Okay, does it go up when I move to X-rays? Yes, it does. X-rays have got a much shorter wavelength, so it is decreasing. But then here's the problem. Visible light has got a longer wavelength than X-rays. So option B is out. Okay, now guys, while you're busy answering these, or if you've already got those answers, guys, jump onto Curio, because, I mean, we've posted up the link. Just get on the webpage, and guys, there's something special for you. There's grade 10 and 11 sections which are actually applicable to you. And obviously what were the codes was PS10 and PS11 and PS12. You can do all 3 of them. But guys, we've noticed something that a lot of you are doing, and guys, we want to give you good feedback. So when you're answering those Curio questions, make sure that you push submit right at the end. Don't skip any of the questions. I want you guys to try every question and click submit. Don't skip them, or you're not learning anything. Okay, now most of you have done those Curio questions. I know that you're good students. Let's get back to our question. Okay, so now let's analyze this next one. Infrared rays. Okay, infrared rays are nice and long waves. Good, that's what we're looking for. Visible light. Okay, slightly shorter. That's good. Ultraviolet, even shorter. X-rays, shortest. Okay, almost short enough to be gamma rays. So it looks like option C is our correct option. What about the last one? X-rays, ultraviolet, visible, infrared. Guys, this just goes the wrong way. X-rays, now that is in the correct order of the spectrum, but what we're seeing is we're going longer and longer and longer wavelengths. So option D is absolutely incorrect. I hope that you can see that we're looking for things which are decreasing in wavelength. So infrared is the longest, down to X-rays, which is the shortest. Option C is definitely the one for us. Okay, now we've got one more question before we end off the show for this evening, and this is also a past paper question. I really like this one because it actually deals with something that you and I deal with every day. It says exposure to sunlight causes damage to skin cells. Now remember what I said, okay, well, certain types of radiation can damage my skin cells. Now, for those of you that love to lie in the sun for a long time with no protection over your skin, guys, now you might say, okay, well, you know, so what, you know, we just got to live once. But guys, you've got to protect your skin, because wrinkles and all of that aging and even skin cancer are the result of some of the skin damage. Even a couple of serious sunburns can increase your chances. So guys, go out into the sun, especially between 10 and 3, especially in the months of October, November, December, and January. Those are the worst months. Okay, you'll notice that the sunlight at that particular time has got a very large amount of what's known as UV. So sunlight is mainly because of ultraviolet rays. And this is the damage that does, or this is the part of the sunlight which actually damages my skin cells. So it's ultraviolet rays. Okay, now it says what type of radiation, okay, now is present in sunlight responsible for this damage? We've already answered this. It's the ultraviolet in the sun's rays which are causing damage to my skin. Ultraviolet is a type of ionizing radiation. It knocks electrons out of my skin cells, does damage down at the cellular level, and then my body has to run around and fix it. So if you've ever been really badly sunburnt, this is the reason why. Ultraviolet rays have gone in and damaged your cells. If it's bad enough, what you'll notice is redness on your skin. Now that's your cells actually programming themselves to open up, and actually they commit suicide on the inside of your cells. It's really horrible. If you look at this under a microscope, if you expose cells to ultraviolet light, the cells actually open up and they actually damage the cells around them. So now UV radiation, very damaging to your skin, ages you, causes cancer. Now it says, name the property of this radiation that is responsible for this damage. Now you might say, okay, well, what is a property of UV? Okay, well, okay, UV is present in sunlight. Okay, now which property am I looking for? Here's a clue. We've mentioned it. UV has the ability to create ions. UV, therefore, is called ionizing radiation. Okay, so ionizing radiation is the bad type of radiation. This is the radiation that I really don't want to go into my body. Now you might say, okay, well, Phil, ionizing radiation also includes X-rays, but what happens when I go to the clinic and they shine X-rays onto me? Isn't that damaging me? Yes, guys, that is damaging you to a very, very tiny amount. And you'll find that the doctors have to protect themselves because they're around the X-rays all the time. So they wear those special coats. Okay, guys, I'm afraid that's bringing us to a close. Unfortunately, I can't ramble on about EM spectrum anymore. I want you guys to play around with your remotes, show your parents. It's a really cool thing to do, and you can actually start seeing different parts of the EM spectrum. That was a great show.
Before we end it, let's just take maybe one question or two.
Oh, fantastic.
Right, here's a simple one from Tsogofa Tsolitlaka. Microwaves are used to send radio signal and TV signals.
Yes, absolutely.
All right, and what kind of electromagnetic radiation could be used to see molecules or a cold virus?
Oh, okay. Now, you've got to be very careful. Now, to answer the last one more completely. Now, microwaves, and especially the shorter wavelengths of radio, can be used to send TV signals. It's usually in the radio band. Cell phones work in the microwave band. Okay, now what they're talking about, what type of electromagnetic radiation can be used to see the cells and the viruses specifically? We're using visible light usually. A microscope is really good to see tiny things. So visible light is a type of radiation that I can use to see things.
All right, that's quite a nice one. Well, the Mindset has also tried the experiment that we had. Otherwise, thank you very much. If you still have some problems, go to our website, which is mindset.co.za/help desk. We'll be there to help you. But otherwise, from us, good luck to everybody that is writing their exams. We love you, and thank you for tuning in. Thank you to Macmillan, our proud sponsor. Peace.